Okay, in this lecture, we're going to be going over how to complete the fourth section of the final project, which is goodness of fit for equal proportions. So I'm going to go ahead and share my screen. Let's see here, share screen. There we go. So this right here is goodness of fit for equal proportions, and I am going to actually kind of start over from the very beginning. I know that I give you all of this, but I actually did a bit more work on this to make the data even better. So I'm going to come over to the data on the Hot Wheels cars. Why? Because, I mean, who doesn't love Hot Wheels cars? So I have all these Hot Wheels cars, and all of these Hot Wheels cars, this is the data that I got with all these different Hot Wheels cars. And each of these Hot Wheels cars has information from Hot Wheels that goes along with it. And for these Hot Wheels cars, they each have what's referred to as a class. And there's different classes because the way that they make these Hot Wheels cars, specifically with this app, is classes are supposed to race in particular races, so on and so forth. And so we're going to show all of these. And so all of these different, let's see here, do I have a filter on something else? Yes, I also have a filter on this. And so I'm going to clear this filter. All of these classes, all these cars have these different classes. Okay, and so you'll see all of these different cars, all of these different classes, and we are going to go ahead and make a pivot table. So insert pivot table. You don't have to actually do this because I actually gave you all of this data already. And so we're going to put this pivot table in there, and I'm going to put, let's see here, over here on the right-hand side, it says class. And so I have A, B, C, D, and S, and then I also have blanks, but we're not going to worry about blanks. And the reason why there's blanks is because those cars haven't gotten a class yet. And so we have these classes right here. And S stands for special. Other than that, I really don't know if these actually stand for anything in particular. They're just different classes. But these are all the classes, or these are all the cars that have been released. So there are 16 cars that are in the A class, 26 cars in the B class, 22 cars in the C class, 21 cars in the D class, and 27 cars in the S class, which to me, that means that they're not so special because literally there's more than any of them. But all that to be said, what we're going to do is we're going to copy this, Control C, and we're going to put it right here. Paste the values, and we have these values right here for a total of 112 cars. And so we've got 112 cars, and with these 112 cars, we want to know, are they distributed equally proportionately, or is there a particular class that is represented more than the other classes. So in other words, this test right here is saying, okay, we have all of these values right here, and we can see that obviously A is represented greater than or less than all the other classes, and S is represented greater than all the other classes. But just because they're represented more or less than all the other classes, does it actually mean that they are statistically represented more or less than all the other classes, which I'm going to change this as well to 112. And so, because what we learned with margin of error is, yes, there's a sample of 16, but there's a margin of error. There's a sample of 26, or this is the value of 26, but there's still a margin of error. And I could actually calculate that margin of error, but that's not part of this test right now. So what I'm going to do, this data allows you to compare the proportionate frequencies of the number of cars between the independent groups based on car class in random sample of 112 cars to determine what independent group of car class has a disproportionate frequency of number of cars compared to the independent groups of frequencies of the number of cars based on car class. So we want to know, are any of these disproportionate to one another? We have the expected frequency of all of them, which is the relative frequency of 0.2, 0.2, 0.2, 0.2. So we have the same frequency expected for all of these. Okay, so we have, because we have a total of 5 car classes. So let's come on over here and say, what is the dependent variable? The dependent variable, once again, is what it's dependent on something else. In other words, what is it that we're actually measuring? We're measuring the frequency of cars. The frequency of cars, which is right here, or the number of cars, the frequency of cars, which is dependent on the car class. So this frequency of cars is dependent on this frequency of cars is dependent on this frequency is dependent on this. And so we've got car class, which this is the independent variable, and it's broken up into 5 different categories, which brings us to what is the independent variable, which is car class. What type of data? It's categorical or nominal. There's no particular order to these, they're just categorical. Then what are you examining or comparing? Once again, with this, what are you examining or comparing? Just come over to here and you can look at the purpose. And you can say, okay, it compares the observed frequencies in the categories to the frequencies that would be expected if the sample data followed a uniform distribution, to determine if the observed frequencies are equally proportionate between categories or groups, to determine what categorical or class differences contribute to the most overall difference between categories or classes. And this is what we're doing right here. I mean, technically you could really say either one of these two, but we're going to do this one right here. And so come right back here where you can literally just copy and paste it, do Control C, put it right here, and paste it into there to determine if observed frequencies of classes of cars are equally proportionate, or have, let's see here, let's write this a little bit better, to determine, yeah, if observed frequencies of cars is equally proportionate between the 5 different car categories or classes, car classes. So that's probably a little bit clearer. Okay, and then next, what is the tail of the test? Right tail test, and the reason why it's a right tail test is because all goodness of fit for equal proportions are right tail tests. But that being said, let's take a look at this and determine why is it that we're running a goodness of fit for equal proportions. So in order to do that, we're going to go to the decision tree, and we need to ask ourselves, are we dealing with continuous data, or are we dealing with frequencies of categorical data? Now, I will tell you, it is possible to use chi-squared with continuous data, but I'm not going to do that to you in this class. The reason why is because you can basically say, okay, we've got continuous data. We just want to make sure that this continuous data follows a uniform distribution, and you can break it up into classes. You can break it up into classes. So I could have, okay, between 100 to 200, and 200 to 400, 400 to 800. And then you can say, what are the number of frequencies for these continuous classes? So you're still looking at frequencies, but you're looking at continuous classes. But we're not going to do that right now. That's something that you can explore a little bit further. There's so much you can do with chi-squared. To be honest, I really enjoy working with chi-squared. I just wanted to make you aware that it is possible, but you're still dealing with frequencies with continuous. So the big thing is you're dealing with frequencies as compared to comparing means. So comparing frequencies, comparing means. So we are comparing frequencies. I'm comparing an observed frequency to an expected frequency distribution. Are the group frequencies expected to be equal? In other words, do you expect all the categories that you have to be equal? And if the answer is yes, then you can do chi-squared goodness of fit for equal proportions. No is chi-squared goodness of fit for unequal proportions. So the answer is yes. So we're going to do chi-squared goodness of fit for equal proportions. And here is how you would do it all the way down, which we're not going to go through that right now because we are going through the example file. So we've got this right here, and we're doing what type of test are you conducting, and we're doing goodness of fit for equal proportions. Okay, so setting up the test. First of all, what is the null and alternative hypothesis? The null hypothesis is there is no difference in the frequency of classes of cars between the 5 classes. So in other words, there is no difference in these 5 frequencies. And the alternative hypothesis is there is a difference in those 5 classes. Okay. Next, what is the test statistic? It's always going to be chi-squared. Oh, sorry, I skipped over. What is the level of significance? I can only have a 1% chance of type 1 error. So in other words, we've got 0.01, then we've got the test statistic of chi-squared. What are the degrees of freedom? The degrees of freedom is the number of classes. So there are 5 classes minus 1. 5 classes minus 1. So that is going to be a total of 4. And then what are the critical values? So in order to do the critical values, we are going to do chi-squared inverse dot right tail, which all the Excel formulas are right here, but the critical value is chi-squared dot inverse dot right tail. Then it's 0.01 comma 4. 4 is the degrees of freedom. 0.01 is the level of significance. Okay. Next, are there any assumptions violated? Once again, just go back to the reference page. Assumption 1, 2, 3, 4. Assumption 1, you have one categorical variable. And right over here, it says, this is what you should use to test this. Bada bing, bada boom. So you can read through that. So there is one categorical variable, and that categorical variable is car class. So you've got these different car classes. And then independence of observation. So in other words, each of these are individual cars. And let's see here, just to show you how much of a nerd I am. I actually got all of these just to be able to do this, but I'm probably going to re-record all of these lectures after this anyway to make it better. But we have all these different cars. And each one of these cars is independent. And so they have their own independent class. They have their own, independent, each one is an independent observation. Let's see here. So they do have independence. The next one, there must be an expected frequency of at least 5 in each category. And so we look at this and we want to just check, is there a minimum of at least 5? And the answer is yes. And the reason why is because they're all 22.4. So they're all greater than 5. The expected frequency is greater than 5. And then the expected frequencies for all categories are equal. And the answer is yes, they are all equal. Okay. Next thing that I'm going to do is I'm going to copy and paste this, Control C, and I'm going to paste, and I'm going to paste the values. So I'm going to go paste values. And I'm going to, I'm going to change the color of this. Let's see here. Okay, so there are no assumptions violated. So I copied and pasted the A, B, C, D, S to right here with the observed frequencies. So these are the actual observed frequencies, and these are the expected frequencies. And you can use this calculator right here. You can use this on your exam, whatever. I would highly encourage you to just keep this around because you can use this to do chi-squared pretty much wherever you go. I will say one more thing about this. The way that I teach chi-squared goes much further than any textbook that you will find, any paper. I actually wrote a paper on this because I was frustrated because chi-squared, the majority of textbooks and whatnot really don't do it justice with what you can do with it. And so basically this column right here, I wrote an entire paper on why it's important to include this one column right here. And so, yeah. Well, really these 2 columns, but anyway. So what is the calculated value of the test statistic? So I know I have 20.94. Let's come over here. It's actually changed, but let's go through this step by step. So I'm going to delete all this. And I want you guys to look at the frequency observed. So this stands for frequency observed, frequency expected. Then this right here is equals frequency observed minus frequency expected. Okay, and then I'm going to bring it down, just drag it down. And you notice that it doesn't have decimal points. I don't really like that. Let's fix this. There we go. So we gave it the decimal points. And then Oh, another thing that you really need to make sure of, this just as a test, do equals sum, and you want to add up everything in this column. And then you also want to equals sum, add up everything in this column. And these two columns should have the exact same sum. Okay. Um, so frequency observed minus frequency expected. So this right here is the observed difference value. It's the difference between the observed and the expected value. Okay. Next, frequency observed minus frequency expected squared. So this is going to bring it into the, it's going to make it positive. Okay. So now we've got the squared value. And we're going to drag this down. And now we are going to do frequency observed minus frequency expected squared divided by frequency expected. So we're going to do equals this value right here divided by frequency expected. And what this is right here is, this is the contribution. Let's contribution of each category to chi-square. Okay. And the reason why it's a contribution is because we are actually going to, once again, equals sum. Going to add all those up. And you'll notice we've got the chi-squared value right here of 3.4464. So we've got the chi-squared value, and we can see that the actual chi-squared indicates that that it's well, I'll show you in just a minute, but we added all those up, so we get the chi-squared value of 3.4464. And if you look at a chi-squared distribution, let me see if I can pull this up. Chi. Oh, let me do this. Chi-square. Okay, so this right here is chi-squared, the two-tailed chi-squared test, but we're really only ever going to do a right-tail test. And so the critical region is over here, so this is a little bit different than what you've been doing. This is probably a better way to look at it, but the chi-squared distribution, and so what we got is somewhere right in here. And then our region of rejection is 13.44 or greater. See if I can make this a little bigger. So 13.44 or greater is what our region of rejection is. But since we got ours at 3 point some odd right there, that's we're able to see, okay, we're not going to reject the null hypothesis. The next thing that we're going to do is calculate the p-value. And the way that we do that, or the probability of getting this value, assuming that there is no difference. So we do chi-squared dot dis dot right tail, and that is G38, which is we put in the chi-squared value. Okay, so we put in the chi-squared value right there, and then we put in the degrees of freedom right there. So the probability of getting this, assuming that there's no difference between these categories, is roughly 48.6%. Okay. And this essentially means that, well, I'll show you. Let's come right over here. What is a calculated value of the test statistic? And we're going to do equals, let's bring it right over here, 3.4464. Okay, so by calculating the chi-squared value by hand, the example, the result was 3.4464. Okay, what is the probability of observing the sample? So we're just going to do equals, come on, equals, and I'll just tell it to update. Right there. I hate it when it does that. Okay, so we've got the probability, which is right there. And then the next thing, what is your decision? our decision is actually now going to be fail to reject the null hypothesis because the calculated test statistic of 3.4464, which it looks like I accidentally, there we go, is less extreme than the critical value of 13.277. We fail to reject the null hypothesis as the results indicated that the frequencies of cars in each class are equally proportionate. Okay. So basically, from what we can tell, there really is no difference between the frequencies of the car classes. Okay. Next thing, these are referred to the next thing that we're doing. These are referred to as post-hoc tests, or essentially these are tests that we're doing afterwards to basically tell where the differences are coming from. Now, the truth of the matter is we didn't find any differences. So therefore, since we didn't find any differences, we really don't even need to run these tests because we didn't find a significant result. However, I'm still going to run these tests. And the reason why I'm going to run these tests is because I want you guys to practice running these tests in the case that you did have a significant result. So the way that we would do this is we do the frequency observed minus frequency expected squared divided by frequency expected. In other words, this column right here. And we divide it by chi-squared. So equals this value right here divided by the chi-squared value. And so we're going to put the $sign right there. So that way I'll be able to drag it down. And we can see that this contributes 53% to the chi-squared value, 17%, and 27%. These are the three that I care about. I only want you to interpret them if they're over 10%, if they contribute more than 10% to the chi-squared value. Okay, so the next thing that we're going to do, so we've determined that this one contributes 53%, this one contributes 17%, and this one contributes 27% to the overall chi-squared value. The next thing that we're going to do is we're going to do equals frequency observed minus frequency expected divided by frequency expected. And the reason why we're doing this is because we're saying this is the percent that it differed from what was expected. Okay, so what this says is this contributed 53%, and this value differed by being 28% below what was expected. This was 16% above what was expected, and this was 20% above what was expected. And something that I like to do is I like to highlight these in green if they're above, just because it helps me to keep up with, okay, what is it that I'm looking at? And then I like to highlight them in, some shade of red. That's just a really, let's do that one. Red if they're below. So if I see red, it's like, okay, they're below. If I see green, they're greater. So we're going to come over here, and the ones that were or the ones that are contributing to chi-squared are A, B, and S. And so I'm going to come over here and I'm going to say, what's your decision? Okay, now interpret percent chi-squared. Now the three classes that contribute more than 10% to the chi-squared values are A, B, and S. Okay, class A contributes, let's see here, 53%. And let's see here, I'm going to just copy and paste this so that way I can. I just want to write it up over here where we can see it all at the same time. Okay, so class A contributes 53% to the chi-squared value and is 28.57% lower than what is expected, with a total with 16 cars in class A. Okay, class B contributes 17% to the chi-squared value and is 16% greater than what is expected with a total of 26 cars in class B. And then class C contributes, or class S contributes 27% to the chi-squared value and is 20.5% greater than what is expected with a total of 27 cars in class S. Okay, so this tells us if there was a difference, this is where the difference would be coming from. Okay, and I'm going to copy Control X, and then X. So that way I'll be able to put it all in here. There we go. So I put all the information in there that basically says where, if there was a difference, this is where it'd be coming from. Okay, then what is the effect size? We're going to come right over here and look at the effect size. The effect size is a different effect size. We're no longer dealing with Cohen's D. We're now dealing with Kramer's V. So it's just a different type of effect size and just not the exact same thing. So what we're looking at is we've got the chi-squared value. We have the total number of observations, which is right there, the degrees of freedom, which is 4. And so now we've got the effect size, which is right here. And the way that we calculate this, I'll calculate this from the beginning. This is the formula right there. So we're going to do equals square root. And then we're going to do the chi-squared value divided by the number of observations multiplied by the degrees of freedom. And notice I put parentheses around the denominator. And then I put parentheses around the total of what's getting square rooted. Then press enter. And then that gives you a Kramer's V of 0.0877. Once again, you're really only supposed to do this if you get a significant result. We didn't get a significant result. So therefore, there's really no point to doing this at all. But you can see that with 4, what we would have is with a sample size, or with 4 categories, degrees of freedom of 4. Sorry, 5 categories, degrees of freedom of 4. This would be a small effect size because it's right there next to the small effect size. So then you'll notice if we have a significant result with a small effect size, the actual difference would not really be noticeable without a statistical analysis. Okay, so we're going to come over here and we're going to say the effect size of, let's do this, equals, that way we can have the effect size right next to us. Right. Okay, so the effect size of 0.0877 is a small effect size. This result indicates that if the results were significant, a large sample size with a statistical analysis would be needed to determine the difference, to determine or observe the difference. So in other words, you would need a large sample size, and even then you'd barely even be able to see the difference. Excuse me. Next, this is what you're doing in your group. What was run, a chi-squared goodness of fit, comparing what to determine if the observed frequencies of classes are equally proportionate. Once again, we're just copying and pasting from up above. Because then what was the result? We're just going to copy and paste this, Control C, and put it right here. the probability of getting this result is more extreme. Nope, that's not true, because the reason why that's not true is 0.48607. Okay, so make sure when you copy and paste that, if you copy and paste anything from my work, that you always update it. It's really easy to overlook it. The results are due to class A being much lower. So give insight about the possible factors influencing this. So what I would write is, although class A, or although, which one is it that, yeah, it's class A. Although class A is less than expected, because the other four classes are pretty close to what to the expected value. It appears as though the frequencies are pretty equally distributed between classes. In short, just because you have one class that's a little lower than everyone else doesn't mean that you doesn't mean that it is significant. You could have just, excuse me, you could have just accidentally, in your sampling, you just didn't get as many observations from that class as compared to, everyone else. And the probability of you sampling like this is, 48%. And so this type of sample could have occurred completely randomly just by chance. Next, talk about the chi-squared and what really happens. So we're just going to copy and paste this. Control C. Okay. And then how should the results be used? The present results indicate that the classes appear to be equally proportionate. And yeah. Next, what we're going to do is we are going to delete this. Let's bring this over here, and we're going to insert, and we are going to do, oh, you know what, I'm going to this. There we go. Highlight what it is that you want. So insert, and then I am going to do this bar chart right here. And then we are going to do of cars by class. So we've got frequencies of cars by class. So the orange is the expected frequency, the blue is the observed frequency, and you literally just have to do that, and it gives you the observed compared to the expected. And then we are able to, which if you wanted to, you could reorder these. It really wouldn't be that bad of an idea to reorder these, but it just can get a little weird trying to reorder those while it's still in there. So I'm fine with it being like this. Okay, so we're going to put that right there. And so we've got the observed compared to the expected, and this really shows you a visual of the distribution. So that is essentially the entire final project for this goodness of fit, and the unequal is extremely similar. The only difference between the equal and the unequal is the expected. So I'm about to do the unequal, and it's going to be extremely similar to the equal. So just be aware, there's really no difference between the two except for how you're calculating the expected. And yeah.